This is part 1 of a review on limits and continuity. In this video, we will focus on finding limits graphically. Here is the graph of function f. For problem number 1, we need to find the limit as x approaches negative infinity of f of x. So approaching negative infinity means let's look at what happens to the value of the function as we go to the left forever. We can already see that the graph is starting to bend down. We don't know exactly what's going to happen after that, but here are a couple of examples. If it went down like this, if it just continued this pattern down, the limit would not exist. So I'm going to put DNE for does not exist. In this case, we are approaching negative infinity, and that does not count as a limit. The only way for the limit to exist as x approaches negative infinity would be if there was a horizontal asymptote. So imagine that there was a horizontal asymptote here at 2, and then this graph came down and approached that asymptote. Then the limit would exist, and the limit would be 2. But we, of course, have nothing to indicate that that's happening, so that's why I'm sticking with does not exist. So another guess that you might have had, you might have seen that this is looking maybe like a periodic function. So in your imagination, you might have said to yourself, well, maybe this is going to repeat this sort of wave process over and over again forever, going up and down between 3 and 1. So let's say that happened. This would still be a limit that does not exist. All right, when the value of a function continues to oscillate forever, that is not a limit either. So either way, the limit does not exist. Number 2, what about the limit as x approaches 1 of f of x? Well, here is the x value of 1 right here. So as we approach 1 from the left, this is what's happening. And as we approach 1 from the right, this is what is happening. So the limit exists because for the limit to exist, you have to be approaching the same value from the left and from the right. Now that value that we are approaching is the value right here, the value of 2. It doesn't matter that function f is not defined at an x value of 1. As x approaches 1 from the left, the value of the function approaches 2. As x approaches 1 from the right, the value of the function approaches 2. Therefore, the limit as x approaches 1 is 2. On number 3, the little plus sign means from the right. So we need to find the limit as x approaches 3 from the right of f of x. Here is the x value of 3. So here's what it looks like to be approaching 3 from the right. So what y value are we approaching? Well, we are approaching a y value of 0. So that is the limit as x approaches 3 from the right. Again, it does not matter that the function is undefined at 3. You see that open circle. We are still approaching 0, and that's what matters. The only way for a one-sided limit to not exist is if there is an asymptote. For example, let's say if we had a vertical asymptote at x equals -3. So the limit as x approaches -3 from the right would not exist because it is not approaching a specific value, it is approaching negative infinity. So this limit does not exist. Number 4, find the limit as x approaches 3. Here is an x value of 3 right here. For this limit to exist, the function has to approach the same value as we approach 3 from the left and as we approach 3 from the right. However, as we approach 3 from the left, the value of the function approaches 2. As we approach 3 from the right, the value of the function approaches 0. Because we are approaching two different values from the left and the right, this limit does not exist. Number 5, is f of x continuous at x equals 1? If not, describe the type of discontinuity. Notice that we are switching gears here. I'm not asking you whether the limit as x approaches 1 exists. It does. We are approaching the same value from the left and the same value from the right. So the limit does exist. But I'm asking you if the function is continuous. Continuous basically means unbroken. And this is a discontinuity right here. You see a hole in the graph when x is equal to 1. There's a hole here. So this is a discontinuity, and a hole is a removable discontinuity. So the answer is going to be C. Side lesson, all other types of discontinuities are non-removable discontinuities. So a jump in the graph like this is a non-removable discontinuity. If there's a break in the graph because we have a vertical asymptote, that is also a non-removable discontinuity. So one more time, the only removable discontinuity is a hole in the graph. Number 6. On the axes below, sketch the graph of a function g that has all of these properties. The function g is continuous for all values of x except for x equals 2 and x equals 4. So our first condition is that the limit as x approaches 2 from the left exists, and the limit as x approaches 2 from the right also exists, but the overall limit does not exist. Here is the x value of 2. If the limit as x approaches 2 from the left exists, that just means that as we approach 2 from the left, we are approaching a specific value. So I'm just going to put a dot here. There just can't be an asymptote. That's about the only limitation. The limit as x approaches 2 from the right also exists. So I'm going to put it down here because I've already seen what's coming. So as I approach 2 from the right, again, I am approaching a specific value. I am going to put an open circle here because it wouldn't be a function if I had a closed circle at 2 different places. So I'm going to leave an open circle here. It didn't matter. I could have made the one on the bottom the closed circle, and the one on the top could have been the open circle. That is not significant. But by making the function approach 2 different values from the left and from the right, I have guaranteed that the overall limit as x approaches 2 does not exist. Focus now on the second property. The limit as x approaches 4 does not equal the value of the function at 4. So the limit as x approaches 4 must exist. However, the value of the function is going to be somewhere else. So I'm just going to put a dot here representing the value of the function at 4. By the way, here's an x value of 4. But I'm going to leave an open circle on the line as it goes through. By drawing it this way, g approaches the same value from the left and from the right of x equals 4. So the limit does exist. And specifically, the limit is 1 because everything at this height has a value of 1. So the limit as x approaches 4 is 1. So I'm just going to put this here to remind us of that. Meanwhile, what is the value of g at 4, which is what this part of the expression represents? Well, g at 4 is 2 because the value of the function is given by this closed circle, which is at a height of 2. So I'm going to put a 2 under here to remind you that the value of g at 4 is 2. We were supposed to draw the picture so that the limit as x approaches 4 does not equal the value of the function at 4. And we have accomplished that because 1 does not equal 2. The last property is that the limit as x approaches infinity should be -1. So as x approaches infinity, that means as we head off to the right, the limit has to be -1. The only way we're going to have the limit as x approaches infinity equal a number is if there is a horizontal asymptote at that number. So here I've drawn it so that as we head off towards the right, the curve levels out and approaches -1. There's a horizontal asymptote at -1. So this drawing of a function g satisfies all three properties.